So here we are, biology students, in Chapter 4, and it's Population Ecology. And there's two sections we'll be discussing. Big idea for the chapter: population growth is a critical factor in a species' ability to maintain homeostasis within its environment. Section 1, Population Dynamics. Main ideas of this section: populations of species are described by density, spatial distribution, and growth rate. Your essential questions for your pop quizzes as well as your tests will be: what are the characteristics of populations and how they are distributed? What are the differences between density-independent and density-dependent limiting factors? What are the similarities between the different models used to quantify the growth of a population? And how does carrying capacity affect reproductive rates? And I'm going to reiterate, this is our fourth chapter, but just to remind you, these aren't the exact questions that are going to be on your tests. But if you're able to answer each of these questions, y to the third power, then you will be fine. The number of organisms per unit area is the population density. 1 bear per several hundred square kilometers, 4 bison, and 10 deer. Dispersion is the spacing pattern of a population. It can be uniform, clumped groups, or random. The pattern primarily driven by resources such as food. And a lot of times people don't find science important, and I totally get it. I didn't get it till I was older, but I get it now. But I can tell you, I have a husband that's an avid fisherman. He's an avid hunter, and I guarantee you he uses science and biology every time he's out there. A species' range is its distribution across the environment. A species might not be able to expand its population range because it cannot survive the abiotic, the non-living conditions found in the expanded region.
Populations of species can be described by density, spatial distribution, and growth rate. One characteristic of a population is its population density. Population density describes the number of organisms per unit of area. Another characteristic of a population is dispersion. Dispersion describes the pattern of spacing of a population within an area. There are 3 types of dispersion: uniform, clumped, and random. One of the primary factors in the pattern of dispersion for all organisms is the availability of resources, such as food. Ecologists study these characteristics to describe populations. Wildlife managers also study population characteristics so that they can protect and manage wildlife and their habitat.
Limiting factors are biotic living or abiotic non-living forces that keep populations from increasing indefinitely. Limiting factors are either density independent or density dependent. Any factor in the environment that does not depend on the number of members in a population per unit area is a density-independent factor. That means it's independent, it's on its own, it's its own merit. It doesn't require anything from anybody. It's totally self-sustaining. Usually abiotic and includes weather events, fire, human alterations of the landscape, air, land, and water pollution. Any factor in the environment that depends on the number of members in a population per unit area is a density-dependent factor, often biotic, and include predation, disease, competition, and parasites. The population growth rate, or PGR, explains how fast a given population grows. Natality is the birth rate of a population in a given year. Emigration, number of individuals moving away from a population. Immigration, number of individuals moving into a population. People tend to use this word right here all the time, okay? It is actually 2 different words. So I emigrated from Illinois, and I immigrated to Missouri. Exponential growth model occurs when growth rate is proportional to population size, and all populations grow exponentially until they encounter a limiting factor. A logistic growth model occurs when a population growth slows or stops. So as you can see, it's kind of slowing here, really grew quickly, but then it just kind of stopped, okay? So population stops increasing for different reasons. When the number of births is less than the number of deaths, or when emigration is greater than immigration, meaning more populations are leaving an area and going somewhere else. Carrying capacity is the maximum number of individuals in a species that an environment can support.
A J-shaped growth curve illustrates exponential population growth. Exponential growth means that as a population gets larger, it also grows at a faster rate. Population growth does have limits, however. The number of organisms of one species that an environment can support is its carrying capacity. Eventually, limiting factors such as availability of food, predators, disease, or lack of space will cause population growth to slow. Under these pressures, the population may stabilize in an S-shaped growth curve.
Species will vary in the number of births per reproduction cycle, age that the production begins, and in the lifespan. Plants and animals are placed into groups based on their reproductive factors. Here you can see the difference between an R and a K strategy. R is the rate of strategy, adapted for fluctuating environment, generally small, short lifespan, many offspring, expend little energy to raise young. So a good example would be mice. Carrying capacity strategy, adapted to stable environment, generally large, long lifespan, few offspring, invest more energy into nurturing young. So think of more along the lines of perhaps an elephant.
If being alive on Earth was some kind of contest, humans, I think, would win it hands down. As a population of organisms, we're the Michael Phelps of being alive, only we have like 250,000 times more gold medals. Last week, we talked about exponential growth, when a population grows at a rate proportional to the size of the population, even as that size of the population keeps increasing. Well, since around the year 1650, the human population has been undergoing probably the longest period of exponential growth of any large animal in history ever. In 1650, there were about 500 million people on the planet. By 1850, the population had doubled to 1 billion. And it doubled again just 80 years after that, and doubled again just 45 years after that. We are now well past 7 billion and counting. So think about this. Today, there are 80-year-olds who have watched the population of their species on Earth triple. So why is this happening? And how? And how long can it go on? Because it's kind of uncomfortable. Let's say you're shopping for dinner, and bear with me, we're going to relate it back to ecology in a second, but you got a lot of choices at your grocery store. You could buy 5 packs of ramen for $1, or you could buy some fancy ravioli made by Italian nuns out of organic pasta for like $20 a pound. They're both noodles, they're both food, but, you know, with the ramen you get more, whereas with the handmade stuff it tastes better, higher quality. What do you do? It's a perennial problem in nature and in our lives, satisfying the two competing impulses. Do I have more, or do I have the best? Quantity or quality? Tough choice. Although we're not really aware of it, all organisms make a similar choice through how they reproduce. In ecology, we size up who chooses quantity over quality by something called the R versus K selection theory. The R versus K selection theory says that some organisms will reproduce in a way that aims for huge exponential growth, while others are just content to hit the number of individuals that their habitat can support. That is, the carrying capacity, and then stay around that level. Species that reproduce in a way that leads to very fast growth are called R-selected species because R is the maximum growth rate of a population when you're talking math talk, as we learned last week. Very strongly R-selected animals make a lot of babies in their lifetime and just hope that they make it. If some of the babies get eaten or something, no biggie. There are others where those came from. On the other hand, K-selected species only make a few babies in their lifetime, and they invest in them very heavily. K in math language is carrying capacity, since K-selected species usually end up living at population densities closer to their carrying capacity than R-selected ones. Of course, things aren't so cut and dry in nature, as most animals aren't very strongly K-selected or R-selected. It's actually, a spectrum. Some organisms, usually smallish ones, reproducing more on the R side, and others usually relatively larger ones on the K side. Most species are somewhere in the middle. So the reason I'm telling you this is to drive home how bananas it is that humans have gotten to the population size we have. Because we tend to reproduce way on the K-selected side of the spectrum. We're pretty big mammals. Usually only have a few kids during our lifetimes, and those kids are a total pain in the butt to raise, but we put a ton of resources into them anyway. So even though humans reproduce K-selected-ishly, for the past few centuries, our population growth curve has been looking suspiciously like that of an R-selected species. And exponential growth, even for R-selected species, usually does not go on for 350 years. So how did this all happen? Well, the short answer is humans figured out how to raise our carrying capacity so far indefinitely, and we did this by eliminating a bunch of obstacles that would have made our numbers level off at a carrying capacity a long, long time ago. These obstacles, you will recall, are limiting factors, and we managed to blast them to pieces in a few different ways. First, we've upped our ability to feed ourselves. Our crazy rapid population growth started in Europe around the 17th century because that's when agriculture was becoming mechanized, and fancy new farming practices like the domestication of animals and crops were increasing food production. From Europe, those agricultural practices and their accompanying population explosion spread to the New World and to much of the rest of the world by the mid-19th century. Another game changer for the human population came in the form of medical advances. Anton Van Leeuwenhoek, father of microbiology, all-around really smart guy, was the first modern scientist to propose the germ theory of disease in 1700, and even though it took about a century and a half for people to take it seriously, it revolutionized human health, leading to things like vaccinations. Suddenly, people stopped dying of stupid avoidable stuff, as they had been for thousands of years, which meant...
Why did people stop dying of stupid, unavoidable stuff? You might want to know that for a quiz.
That everybody lived longer, childhood survival rates improved, and those kids went on to make their own babies and get very, very old. And we also... Even though the human population continues to grow, the rate of population growth actually peaked around 1962 and has been declining ever since. At its peak, the human population was growing at about 2.2% per year, and these days it's declined to about 1.1%, and it's still falling. Families in most industrialized countries are getting smaller and smaller. But why? Well, part of it has to do with women. As women in developed nations get more education, they're having babies later in life, and when an animal doesn't reproduce to its fullest potential, meaning it doesn't start having babies as soon as it's, sexually able to, that animal is going to have fewer offspring. Also, if you give women more choices and more education, they might be liable to choose a second career in astrophysics rather than becoming a mother. Another reason for the falling population growth rate has to do with the way that we live our lives. Back in the early 20th century, more of the world worked on farms and maybe ate their own food. Kids were a real asset to a farm back then. It's a good example of that idea about more hands doing more work to increase the carrying capacity of the human population. Yeah, kids were extra mouths to feed, but they were also a really important workforce, and you could just feed the kids the stuff you were producing. That's what we call a positive feedback loop. As the population grows, the workforce gets bigger, and the place, as a result, supports more of us. But these days, that's not happening so much anymore. More and more people are living in cities where you don't need kids to help with the crops.